Hello everyone. Today in this video we are going to talk about different kinds of charge distribution. So after this video you should be able to define different types of charge distribution and write their units, and you should be able to derive the expression of force due to different kind of charge distribution. So we already know if there is two charges separated by distance r, then we can use Coulomb's law to find the force, and if there are multiple charges we use superposition theorem. But what if the charges are making some shapes, like suppose we have many charges and they are in the form of line, so we call it line charge distribution. Distribution means how the charges are distributed, and we can see in this distribution they are making the line, so it's a line charge distribution. So this is the definition. If the charges are in the form of line, then we call it line charge distribution. And another term is line charge density. Charge density is charge per unit length, that is charge divided by length. We denote charge density by lambda. Now we can find the unit. So for charge it's coulomb and for length is meter. So unit of charge density is coulomb per meter. So now we'll find the force due to line charge distribution. So we are considering a positively charged line conductor, and suppose this length is dl, small length, and the charge of this part is dq, and at a distance of r from this point I'm keeping a test charge. Test charge means a small positive charge, and we denote test charge by q0 or q0. So now from the diagram, dl is small length and dq is charge of this length dl, and we already know the line charge density lambda is given by charge by length. So out here our charge is dq and length is dl. So if you put the values, and dq will be dq is equal to lambda dl. So using this I am finding the charge, because to use Coulomb's law we need two charges. So q0 we already have, and we need to have the value for dq. So there will be force between this dq and q0, and this can be given by Coulomb's law. So force, small force, that is df is equal to 1 by 4 pi epsilon naught q0 dq divided by distance square. So for this dq I can use lambda dl. So if you put this, then now this df is the force due to small part of the conductor out here. So if you want to find the force due to whole length of the conductor, you have to add all the forces due to each length dl. So for that we do integration. Integration means we are adding all the forces due to small length. So the total force due to entire length is given by f, that is integration of df. So if you put the value of df, you will get this. So the total force will be given by this expression. So this is the final expression, and if you want to write it in vector form, we just need to put cap out here and we have to give the direction out here. So this is the vector form. So this is the derivation for force on a charge due to a line charge distribution. This is the next case. Suppose these charges are at the surface of a conductor, then we call it surface charge distribution. So all the charges are distributed on the surface of a conductor. So the definition of a surface charge distribution is charges distributed over the surface of conductor. Surface charge density is the charge per unit area of surface charge distribution. So if we divide the charge by area, we get the surface charge distribution. So it is the charge per unit area of a surface charge distribution. In a surface charge we are interested in unit area, small area. So surface charge density is given by sigma, that is charge by area. So now the unit of charge is coulomb and unit of area is meter square. So coulomb per meter square is the unit of surface charge density. Now we will find the force due to surface charge distribution. So I'm considering a surface, positively charged surface. Out there I'm considering a small area ds, and dq is the charge of that area ds. Then at a distance r from this point I'm considering a test charge q naught. So now from diagram you can write this. Now we know surface charge density is given by sigma, that is charge by area. Now out here charge is dq and area is ds, so dq will be sigma ds. We are finding dq because I want to find the force between this charge and this charge. So now the small force between this q naught and dq will be given by this expression, and we know dq is sigma ds from here. So I can write the small force due to this part of the conductor is this much. Now in order to find the force due to whole conductor, I have to keep on adding all the forces due to small area like ds. So we have to integrate with respect to ds. So, and if you put this out here, you will get this. So the force will be given by this expression, and this is the final expression. And if we want to write it in vector form, we just need to put cap out here and the direction out here. So this is the vector form of force between a surface charge distribution and a test charge q naught. Now the next case, these are the charges and they are making one solid volume. So they are distributed over volume, so we call it volume charge distribution. So volume charge distribution is defined as the charges distributed over a volume of a conductor. Amount of electric charge per unit volume of a charge distribution is called volume charge density, meaning volume charge density is given by charge by volume. So unit of volume charge density is charge and unit of volume is meter cube, so coulomb per meter cube. So now we'll find the force due to volume charge distribution. So we are considering a volume that is positively charged, and inside this volume I'm considering a small volume dv, and suppose the charge of this volume is dq. So at a distance of r from this volume I'm considering a test charge q0, and I want to find the force between this q naught and dq. So first I'll find dq. From the diagram, dv is the small volume and dq is the charge of small volume dv. So we know the volume charge density is given by charge by volume, so rho is the volume charge density. Now I can write dq is equal to rho into dv. Now the small force due to this dq on q naught will be given by this expression, and df means small force, and if we put the value of dq here, then we get df is equal to this expression, and this is the force on this q naught due to dq. And if we wish to find the force due to entire volume charge distribution, then I have to add all the small forces due to all the volume dv present in this distribution. So for that I have to integrate. So the total force on q naught will be integration of this df. So when you put the value of this df from here, then you will get this. So this is the final expression of the force on this q naught due to this entire charge distribution. Now in vector form I have to give the direction, and direction is along the unit vector r. Now let's understand what is charge density one more time. We know the density means of how heavy is an object. Like if the molecules are more packed, the object is more dense as compared to the object with less dense molecules. Similarly, charge density gives the idea how packed the charges are kept. For example, if you see these two line charges out here, charges are closely packed, and out here they are loosely packed. That means out here charge density is more. So for that, lambda, that is charge density, is higher for this and less for this. Similarly, out here you can see surface density of this diagram is more as compared to this, because out here we have more charge at the same area. Similarly, if you consider this, out here you can see there is more charge in the same volume as compared to this. So out here rho, that is volume charge density, is more. So charge density represent how packed the charges are kept. So now let's summarize the video. So line charge density means charge per unit length of a conductor, and the formula is charge by length, and unit is coulomb per meter, and the total force due to line charge density is given by this expression. And surface charge density is charge per unit area of a charge distribution, and surface charge density is given by charge by area, and it is denoted by sigma, and unit is coulomb per meter square, and this is the expression of force. And this is the volume charge density, that means charge per unit volume, and volume charge density is given by charge by volume, and rho is the symbol, and unit is coulomb per meter cube, and total force is given by this expression. So out here everything is almost similar, only we have to change linear charge density, surface charge density, and volume charge density, lambda, sigma, and rho. And this is the end of the video. Please like the video, and please give your suggestions through comment. And if you are new to the channel, please subscribe it. And out here is my phone number, and if you want help in any topic, please WhatsApp me on this number. I will try my best to help you. Thank you.